Greetings. This is the third lecture in Chapter 20, more about oxidation reduction reactions. This little creature is a bear cat. We'll go to the next slide. That deep emotional conviction of the presence of a superior reasoning power which is revealed in the incomprehensible universe forms my idea of God. That was said by Albert Einstein. Okay, today we're going to look at some practice problems. Then we're going to look at hydroxylation of alkenes, mainly diols, oxidative cleavage of 1,2-diols, and oxidative cleavage of alkenes or ozone lysis, permanganate cleavage of alkenes, oxidative cleavage of alkynes, and the use of functional group interconversion in designing a synthesis as we proceed to the end of Chapter 20. But first, here are a couple of review problems. Actually, I think there's 5 or 6 of them. I'm going to let you work them out, although I'm going to give you some idea of what the correct answers are. You're not going to see them on the slides. But draw the major organic product generated in the reaction below. Pay particular attention to the regio and stereochemical details. Here we've got molecular hydrogen, palladium, and the molecular hydrogen is going to be added to the carbon-carbon double bond in the presence of a metal catalyst, palladium. This is catalytic hydrogenation. It's going to be the addition of molecular hydrogen in a syn addition, S-Y-N. In reality, what's happening is a reduction, and I can describe it. The double bond's going to go away. And we're going to put a proton on that carbon and a proton on that carbon to form the product. You can write it with stereochemical detail and having methyl groups, these 2 methyl groups on one side of the carbon-carbon bond, and the hydrogen atom, one of them that's on this carbon facing away from the plane of the screen, and another constituent on this carbon right here also away from the screen, the plane of the screen. It could be CH2, CH3, this component going behind the screen, and a proton going behind the screen on this side, and then these 2 CH3 groups will be pointing towards us or on the side facing the screen. Okay, let you determine your structure, and you can come to your answer also. Here's review. Problem 4, provide the major organic product of the following. We have an imine being reduced to an amine compound ultimately. Catalytic hydrogenation is used to reduce the carbon double bonded nitrogen multiple bond right here. So we're going to put a carbon, rather a hydrogen here and a hydrogen on the nitrogen and form an amine undergoing reduction. The carbon nitrogen double bond becomes a carbon nitrogen single bond. Okay, and I'll let you write your own product. Review problem 5. Which of the following alcohols is oxidized to a ketone by chromic acid? Okay, now we got to go through these 1, 2, 3, 4, 5, take a look at them. But basically, you should know that a secondary alcohol is oxidized to a ketone by chromic acid. So we just need to go through here and identify a secondary alcohol to start with. Now this one here is a tertiary alcohol because this is the benzene ring, and probably a double bond right there, right over here and right there. So we know that that's going to be tertiary. It cannot be oxidized to a carbonyl group because there's no hydrogen on the carbon to which the OH is bonded, that one right there. In this case over here, this is a primary alcohol, so we can eliminate it. Chromic acid with a primary alcohol is going to form an aldehyde and then a carboxylic acid. This one down here, what kind of alcohol is this? Obviously, it is a tertiary alcohol. And let's see, let's go to this one here. Now this one, voila, it is a secondary alcohol. What about this one? This is a primary alcohol. So 2 is the answer right here, 2. and we're undergoing oxidation in this particular reaction. Okay, practice problem 6. Provide the structure of the major organic product in the reaction below. So we have a primary alcohol, PCC, pyridinium chlorochromate. It's a chromic anhydride, and an equivalent of HCl dissolved in pyridine will form PCC. PCC is a mild oxidizing agent used to convert alcohols to aldehydes. So, provide the structure of the major organic product. So we're going to get an aldehyde. We're going to undergo oxidation. This carbon becomes the carbon of a carbonyl group, and we have a proton remaining on the carbon, forming an aldehyde. Okay. Problem number 7. Provide the major organic product of the following. Okay, here we have a primary alcohol, and we have our oxidizing agent, chromic acid, here, and we're going to form a carboxylic acid ultimately. It's actually a two-step process. First, we're going to form an aldehyde, and then with further oxidation, we'll form the carboxylic acid. So this carbon right here is going to become a carbonyl carbon, and we'll have a proton bonded to it. So we have CH2C of a carbonyl group with one proton forming the intermediate aldehyde, and then with further oxidation, it becomes a carboxylic acid. Okay, the last practice problem or review problem. Which of the following oxidizing agents is used in a Baeyer-Villinger oxidation? Now, you may remember, you just have to remember that peroxy acid is used to oxidize an aldehyde or ketone, and if it's an aldehyde, it forms a carboxylic acid. If it's a ketone, it forms an ester in the Baeyer-Villinger oxidation reaction. So just looking at these possible selections, here is our peroxy acid. So E is the correct answer. Okay, now let's get into some examples of oxidation. We're going to continue our discussion of oxidation reactions involving organic compounds as we complete chapter 20. As you know, an alkene can be oxidized to 1,2-diol in two different ways. The first way is shown on this slide, using potassium permanganate in a cold basic solution. An alkene can also be oxidized by osmium tetroxide, as shown on the next slide. Osmium tetroxide was the subject of a recent article that I wrote in Toxic Tips, and I did this with a student as a co-author. It's in an American Chemical Society journal called Journal of Chemical Health and Safety, which I've been doing for a long time. And I select an organic compound actually 6 times every year. And if you're interested in co-authoring an article with me, you can enroll in the course. It's a 1-hour course called Chemical Safety and Health in the fall. But here we go. Here's the reaction that we're talking about. 2-butene undergoing oxidation, forming a vicinal diol, or 2,3-butane diol, a glycol type molecule. The 2-butene is oxidized to 2,3-butane diol with potassium permanganate. If the reaction were heated, or if it were put under acidic conditions, the diol would be further oxidized, as we'll see in section 7 of the chapter later on. A vicinal diol is formed because OH groups are on adjacent carbons in the 1,2-diol. A diol is also called glycol, so sometimes the components are called vicinal glycols. Okay, let's go to the next slide. Now here is what I was talking about using osmium tetroxide, OSO4. This is the second way alkenes are oxidized to 1,2-diols. 1-butene, over here on the left, is oxidized to 1,2-butane diol with osmium tetroxide. And again, a vicinal diol is formed. Notice these two carbons are adjacent, both have OHs. This is, again, an oxidation reaction. Here is the mechanism of cis-glycol formation, starting with a cycloalkene. Both potassium permanganate and osmium tetroxide form a cyclic intermediate when they react with an alkene. Both are in a highly positive oxidative state and attract electrons. Manganese is +7 and osmium is +8. Formation of the cyclic intermediate is a syn addition, SYN, because both oxygen atoms are attracted to the same side of the double bond, which you can see right here. This oxidation reaction is also stereospecific since a cis cycloalkene forms only a cis diol, which you can see the product. So we have a cis cycloalkene, we have the potassium permanganate, and we have the intermediate formed. Side reactions, by the way, can occur due to this negative charge right here, although we're not showing any on the slide. And then we form the cis diol. Of course, all of this is oxidation. So cyclopentene forms a 5-membered cyclic intermediate with permanganate ion, is hydrolyzed to cis-1,2 cyclopentane diol as the final product. Okay, let's look at the next slide. Here is the mechanism for cis-glycol formation with osmium tetroxide, right here. Cyclohexene forms a 5-membered cyclic intermediate with osmium ion. It is hydrolyzed to cis-1,2 cyclohexane diol. When the cyclic osmate intermediate is hydrolyzed with hydrogen peroxide, H2O2, osmium reagent is reoxidized back to osmium tetroxide. Therefore, this expensive and toxic oxidizing agent is used in catalytic amounts. Okay, and you can see here's the cis-cycloalkene and the cis-diol that results from this oxidation that occurs. Higher yields of the diol are obtained when osmium tetroxide than with potassium permanganate because the cyclic osmate intermediate is less likely to undergo side reactions. Okay, let's look at one more. Here is cleavage, oxidative cleavage of 1,2 diols. Why is this called a cleavage reaction? Because it cuts the reactants into 2 pieces. There it is, 1 piece over here, 2 pieces. As you can see, the 1,2 diol is oxidized to a ketone, acetone, and an aldehyde, ethanol, by periodic acid. Iodine is a highly positive oxidative state, +7, so it readily accepts electrons. So 1,2 diol in the form of 2-methyl-2,3-butane diol, this is our cyclic intermediate, and of course acetone and ethanol undergoing this reaction. Overall, it is an oxidation. So the periodic acid reacts with the diol to form a cyclic intermediate, and as the cyclic intermediate breaks down, the bond between the 2 carbons bonded to the oxygen breaks. If a carbon was bonded to an OH group, it is also bonded to 2 R groups. The product would be a ketone on the left. If the carbon is bonded to a R group or a proton, the product will be an aldehyde that you see on the right. Here we see 2-methyl-2,3-butane diol being oxidatively cleaved into acetone and ethanol. So periodic acid, HiO4, cleaves diols into aldehydes and or ketones. Okay, we're going to stop right here. This is part A. We'll start with part B in just a second. Thanks.